So we have talked about solving equations and inequalities, including absolute value inequalities, which are simply just different types of compound inequalities. I want to now talk about how to solve polynomial inequalities. And a good example of this is something that you see right over here. So this is an example of a polynomial inequality. So now we're seeing that we have a degree greater than 1 on one of the sides of the inequality. So we're going to look at how to approach something like this. So I went ahead and I wrote out the steps for solving a polynomial inequality, which I'll allow you to kind of pause the video and review or write down on your own if you need to. But the steps are pretty much as follows. We are going to get 0 on the right side of the inequality. And I've highlighted the right side just because I want to make sure that we are having our inequalities face the right way, that we don't have to switch anything around or cause any bigger issues for us later on down the line. So we're going to get 0 on the right-hand side, and then we're going to solve this inequality like it's an equation. And after we've done that, and we've found the zeros by solving our little equation here, we're then going to test the intervals of our solution set. Because if you remember, the solutions to an inequality are a range or an interval of values. There may be multiple values that satisfy that inequality. So let's go through this step by step. So for the first one here, let's take a look at this problem. So the first thing I'm going to do again is I'm going to isolate all my non-zero terms to one side. So I'm going to subtract 16 from both sides, which gives me the following inequality. So I've got that. Now, I'm going to solve this like it's an equation, which I can see that I can factor. So this is x minus 7, x plus 1, and I'm going to set this equal to 0. So I'm just temporarily solving this like it's an equation, which gives me the following zeros, positive 7 and negative 1. Now, what you don't want to do here, and I'm going to write this in red to ensure that you don't want to do this, you don't want to just slap on an inequality symbol there. This doesn't actually make any sense here. That's not what we want to do. So don't do this. So now that we know not to do that, I'm going to erase that. Instead, what we want to now do is we want to think about, okay, these represent the places where my quadratic here are going to cross the x-axis, which will allow me to quickly identify where is my quadratic greater than or equal to 0? Where is this going to be greater than or equal to 0? So there's two ways that we can do this. The first is to just graph this. And you could just pull up a graphing calculator right now if you'd like, but this actually is a pretty straightforward quadratic to graph. We know that our quadratic is, or a parabola, is going to cross the x-axis at -7 and positive 1. I also know that my leading coefficient here is positive, which means my parabola is going to open upwards. So this is just a rough sketch here. I'm not trying to do anything too complicated here. That's not a great parabola. I'm going to fix that. So that's not a great parabola still, but you get the idea. I can see that my parabola is going to be crossing the x-axis at -1 and positive 7. So by looking at this here, I'm asking myself, when is my quadratic going to be greater than or equal to 0? And I see that it's greater than or equal to 0. It's above the x-axis here and here, where I've just highlighted. Now, what do I write for my solution? I want to write the x values. Let me change my color here. I want to write the x values where that cause this inequality to indeed be true. So where is that happening? It's happening from negative infinity up until -1. So I'm going to put a bracket there. And from positive 7 to positive infinity. So if I write my solution in interval notation, I would say negative infinity to -1, bracket, union positive 7 to positive infinity. And so I can then just box my answer here like this. Okay, so what I've just done is I've graphed my my polynomial to see where it's crossing the x-axis. That's what I did here. But then I'm just looking at my graph to identify where is my quadratic going to actually be greater than or equal to 0 there. Now, what if I didn't have access to a graphing calculator or I didn't know how to graph? Well, I can always just numerically test as well. That is to say, I could look at my number line and I could try plugging in a value in this interval, try plugging in a number in this interval, try plugging in a number in this interval, and just test. So for example, if I want to start with this first interval, I could try plugging in something like x is equal to -2 because it's less than -1. When I try plugging in -2, and I'm just going to plug it into this part here, when I try plugging in -2, what do I get? -2 minus 7 is -9. -2 times -2 plus 1 is -1. Well, that's equal to positive 9. Is that greater than or equal to 0? And the answer is yes. Therefore, this interval does indeed work. Any value in that interval works. Well, let's try an interval number in the next interval. Suppose we chose something like 0. When we plug 0 in, we get -7. 0 plus 1 is +1, which is -7. Is that greater than or equal to 0? And the answer is no, it's not. So this interval here doesn't work. And then finally, I could try plugging in a number into this interval here. So we'd say x is equal to 8, for example. 8 minus 7 is 1. 8 plus 1 is 9, which is equal to 9. Is that greater than or equal to 0? And the answer is yes. So this is just another way of going about and testing your intervals. Okay? So if we were to then look at something like this, you'll notice that a problem like this, if I go ahead and start moving all the non-zero terms over to one side, I see that no matter what I do, there's not something I can factor here. Now, later in the course, we'll actually look at something called the rational roots theorem, and we'll use something called synthetic division to actually find the zeros here. But without access to the rational roots theorem, at this point in the course, all I can really do is just graph this. And I'm not going to do a super detailed graph, but it does end up looking something like this. It's going to just look something like this. We're going to go up, down, and something like that. And again, if you have access to a graphing calculator right now, you can see that my cubic function here is actually going to be less than 0 in these spots. So what do I write for my intervals? I'm going to go everything from -infinity to -3, parentheses. I'm going to write a union symbol here. Then I'm going to go from -1/2 to +2, and I'm going to fill in everything here because those are the x values that cause my polynomial to give me a graph that's below the x-axis, that is less than 0. So this would be my interval here. Okay. Now, similarly, if you have access to a graphing calculator right now, pull one up or just maybe use an online graphing utility like Desmos. For number one, here, I want to talk about a couple of unique solution sets and how to express those solutions using interval notation. So for this first graph here, you're going to get something that looks like, actually, let me see if I can actually pull this up. Let me pull this up here. And while I'm at, okay, so let's suppose I had something like x squared plus, x squared plus 2x plus 4. Well, if we look at this graph here, we're asking ourselves, when is this graph going to be greater than 0? And the answer is, well, always. It's always greater than 0. So for every x value that I plug in here, I'm going to get something that is greater than 0. So how would I express my answer in interval notation? I would write from -infinity to +infinity. Now I'm going to make that a little bit easier to see. So now let's look at the same graph. Now we're asking ourselves, when is this graph going to be less than 0? Well, the answer is never. So there's two ways to express that. We can just say something like this, just to indicate that it's never less than 0. Or we could also write something like this here. And this is what's known as an empty set, or just another way of expressing to say that there are no values that satisfy this inequality. Now over here, if I were to look at something like this, let's go ahead and put that graph in. Looks pretty similar. Okay, now let's look at this graph. A little bit different here. I'm going to zoom in on that a little bit. Now, we're asking ourselves, when is this going to be less than or equal to 0? Pause the video and think about this for a second. Well, the answer is there's only one place where this is going to be less than or equal to 0, and that's at -1. So you can either write your answer like this, or if you just said x is equal to -1, that would be fine as well. There's just a single value where this is true. Now, let's move this over here just so we can see this. Oops. There we go. Now what about number 4 here? Let's look at number 4. The same graph, when is this polynomial going to be greater than 0? Well, pretty much every place except for -1. So here we can say something like -infinity to -1 union -1 to +infinity. So a couple of different unique solution sets here that we should be familiar with. Let me see if I can pull this back. Awesome. All right. So a couple of different ways to express some of these solutions. The final thing I want to talk about in this lesson is how to find the domain of an expression, or in what we'll start exploring functions. So first off, what does it mean to find the domain? The domain is the set of all x values for which the function, and I'm just going to write f of x for function, for which the function is defined. So in this example here, if I want to find the domain of this particular function, what is the only thing that must be true here? Or what's the main thing that must be true, I should say? We know that our radicand, or anything that's underneath the radical sign, must be greater than or equal to 0. So this statement that I'm about to write, or I'm writing right now, has to be true. So now that we've talked about finding polynomial inequalities, or how to solve them, we can actually do this. So let's factor out the 3 here. That's 25 minus x squared, greater than or equal to 0. And I'm going to just solve this. I can divide both sides by 3 right now. And so now I've got this. And I can solve this. I can factor minus x. 5 plus x is equal to 0. Just solve it like an equation. And I get the following zeros. I get x is equal to positive 5 and negative 5. And if I were to graph this polynomial, I would see again, it's a quadratic with zeros at negative 5 and positive 5. And I see that my parabola is going to be facing downward. So when is this going to be greater than or equal to 0? Everything from here to there. So my domain would be from negative 5 to positive 5. Okay? I encourage you to pause the video and try B. And for this one, hopefully you found that the domain is all real numbers. And I want you to think about why.